morning, everyone. I hope you're well. Today is the third day of our Senior Researchers Workshop. And today with us is Carley Iles from Cicero Institute, and she will help us understand the attribution of extreme events and guide us through the practical part and the exercises that she prepared. So I think this will be really interesting to see how we can use the online tool for and for the analysis and for obtaining some meaningful and useful results. So without any further ado, please, Carley, the floor is yours.
Thanks, Biljana. Okay, I will share my screen. So you see it, okay?
Yes.
Okay. All right. Yes. So today is going to be all about extreme event attribution. So this is actually a repeat of what I did for the early career researchers. So, I mean, if you've already seen all of that, please don't feel obliged to stay for the whole thing. Of course, you're also welcome if you want to listen again. That's fine. So the schedule is so the lecture parts will take around 1.5 hours, depending on how fast or slow I go, and there'll be 2 parts with a break in between. So the first part is looking at what is extreme event attribution and the main approaches, and then the second part is looking at some more detail, the main steps involved in an attribution analysis, and then the practical is attributing the 2007 Serbian heatwave using Climate Explorer. And I've put a second example, which we probably won't have time for, but just in case anybody wants to see a second example, the instructions are also there about the Danube and LB heavy precipitation and flooding in 2013, just as an example of a different kind of event. Okay, so I start by going through what is extreme event attribution. So it has to do with looking at the causes of extreme weather and climate events, specifically, in our case, looking at how climate change or human-induced climate change has affected a given event. So an extreme event can be something like a heat wave, a cold wave, heavy rainfall, floods, hurricanes, snowstorms, and so on. And then attribution, so this is a definition taken from the IPCC. It's defined as the process of evaluating the relative contributions of multiple causal factors to a change or an event with a formal assessment of confidence. So for us, the question we're looking at is, what role did human-induced climate change play in a given extreme event? So after an extreme event happens, say there's a heat wave or there's some flooding or whatever, people often ask the question, was this event caused by climate change? And this is not an easy question to answer, in that it kind of suggests it's sort of binary yes, no. So we can't attribute whether a specific event was caused by climate change or not, like in this yes, no sort of way, because extreme events tend to be caused by a combination of factors acting together, and climate change might contribute, but it's not generally the only thing. And also extreme events can happen in a world without climate change as well. So we can change the question a bit. So how did climate change affect the probability or magnitude of this kind of event? So now we're looking at it in a probabilistic way, and we're looking at this kind of event, so maybe not just the specific events, but also events similar to this event. And we are able to answer this question. So this event attribution science has been around for about 15 years, so it's quite young as far as science goes. So the techniques have been developed a lot over the recent years. another way of thinking about this extreme event attribution question is in terms of dice. So if you roll the dice in a natural climate, the dice are not loaded, so you get a 6, 1/6 of the time. Whereas in the present day climate, it's like the dice are loaded, so now you roll more 6s than you would expect. So we can look at how does the probability of rolling a 6 change between the two sets of dice or between the two climates. Okay, so going back to climate, so here's a probability distribution function of something. Let's say it's summer mean temperature. So most summers are average, but then you get a few which are very hot and a few which are very cold. And hang on just a second, I need to move this out the way. Okay. So climate change can affect these distributions in a number of ways. So for example, the mean can shift. So in this case, if the mean of the distribution shifts hotter, then you tend to get more hot extremes and less cold extremes. If the variability changes, so in this case, the distribution is now more spread out, then you get more extremes of both types. And another way it can change is the symmetry. So in this case, this also affects a bit how many extremes you get. So this might depend, how this change might depend on which variable you're looking at. So this whole extreme event attribution idea started with a paper by Miles Allen back in 2003, in which he explored the question of liability for climate change. Will it ever be possible to sue anyone for climate change? And the context which led him to think about this was some floods which happened in Oxford, where he lives, and so the water got rather close to his front door. So that led him to ask himself the question of whether you could ever claim compensation from the emitters for the decreased value of his house now that it's more prone to flooding than it would have been. And so in order to answer this, you have to know how the probability of this kind of flood has changed due to climate change. And then you could look at it like this. So if the probability of a flood increases tenfold due to greenhouse gases, then 9 out of 10 floods would be due to climate change. Or alternatively, you could think of it that you could attribute 90% of the damages of a flood to climate change. And then the first actual study doing extreme event attribution was the Stott et al. 2004 paper. They looked at the 2003 European heatwave, and they say this was a really bad heatwave. I think there were 70,000 deaths or something like that. And he found that the probability of this heatwave had at least doubled due to human influence. And since then, there's been many extreme event attribution studies. So some of them are published in this BAM supplement explaining extreme events of the previous year from a climate perspective. So the first was in 2011, and it had 6 studies, but more recent editions have 20 to 30 case studies. And on this map, this is showing all the extreme event attribution studies published to date. This is from the Carbon Brief website. So you can see there's been a lot of extreme event attribution studies, but their geographical coverage is not very even. So you have more studies in the US and Europe and Southeast Asia and Australasia, and not so many in places like South America or Africa, for example. But there are some efforts to try and even this out a bit. Okay, these two people have been very important in extreme event attribution science. So I put these in last time because they were listed in the Time list of the 100 most influential people of 2021 for their work on extreme event attribution. Yeah, so this is Freddie Otto, this is Gert-Jan van Oldenburg. Unfortunately, Gert-Jan actually passed away the day after the workshop. So early career researchers, but a lot of stuff in this lecture will be based on his work, and also he is the person behind Climate Explorer. So he's been very influential for what you're going to hear today. Okay, so how do we do an extreme event attribution study? So I'll explain the concept. So we're looking at how has the probability of a given class of events changed between the world as it is now. So this is often called the factual or the actual world, compared to the world that might have been, otherwise called the counterfactual. So the simplest way of doing this is you simulate the world as it is, so with observed concentrations of greenhouse gases and so on, and simulate also the world that might have been, so with, say, pre-industrial greenhouse gases, and you count the number of events. In reality, you simulate both worlds multiple times in order to get a big enough sample size. So, for example, an event could be something like a heat wave in a given region over a certain temperature threshold, say 35 degrees, for example, or yeah, you can choose a threshold. And then, so this is just a visual representation of this is the world as it is now, and these dots are supposed to be heat waves over the temperature threshold, and here's the same with the counterfactual. So you see you have more heat waves in the factual than the counterfactual, and then you can use this to make a probability ratio. So this is kind of the main number that comes out of extreme event attribution studies. It's sometimes known as the risk ratio. So it's basically the probability in the factual world divided by the probability in the counterfactual. So if I had an event which was a 1 in 5 year event now, and it used to be a 1 in 10 year event, then my probability ratio would be 2. So it's become twice as likely as it was. A 1 in 5 year event is not particularly extreme, so maybe we would be looking at more extreme events than that, but it's just to illustrate the idea. And you may also see results expressed in terms of fraction of attributable risk. So this is calculated as the probability in the world as it is now minus the probability in the world that might have been, divided by the probability in the world as it is now. So in this example, we end up with a fraction of attributable risk of 0.5. So you can think of this as if half of the risk of your event happening is due to climate change. So here's an example. This is the Russian heat wave, which happened in 2010. So this is showing a map of the event. So this is for July 2010 compared to an average July. So you see that it got to up to 6 degrees hotter than usual in places, and this caused 55,000 deaths, and crop production went down by 25%, and there were lots of economic losses as well. So you can simulate this event with climate models, with present day greenhouse gases and so on, and then also again, in this case, they actually simulated it for an earlier period. So they simulated the current climate was 2000 to 2009, and then the earlier climate was 1960 to 1969. And so they do lots of simulations of both of these. And then these are the results. I'll just explain this graph. So we have temperature on the y-axis and then return period on the x-axis. So return period, if it's 100, that means the event happens once every 100 years. So the return time is 1 minus the probability, or you can also calculate it as the sample size divided by the rank. And so we have two sets of curves here. So this is the current climate, this is the earlier climate, and each circle is a July. So we can use this to look at the return time for our event. So this is the observed event. So it was a bit under 25 degrees. That might not sound very hot, but it's just because it's been averaged over a spatial kind of area and over the whole of July, and it's a daily mean temperature rather than maximum, so that kind of makes it look cooler than it actually was. So you read across here, and then when it crosses this curve, you read down, and so the event was a 1 in 40 year event. And then you can also do the same for the curve for the earlier climates. So now you read down, and it's approximately a 1 in 100 year event. So the probability is actually increased by about 2.5. Another way of looking at it is in terms of the magnitude. So now we're looking vertically. So you see that this curve is approximately 1 degree above this curve. So the heat wave was about 1 degree hotter than it would have been. And you can look at this as a fraction of the overall anomaly. So here, this is the temperature of an average July. And then you can see that, say this was 6 degrees or 5 degrees hotter than average. And then maybe about 1/5 of this was accounted for by climate change. So, so in this case, we have a small increase in magnitude and a large increase in probability. And after this event happened, there were actually 2 studies about it where the results appeared contradictory, because one said that climate change had only had a very small influence, and the other one said that it had had a large influence. And this can actually be due to differences in how you're looking at it. So it's important to record like the way you're approaching this. And often studies will quote both the change in magnitude and the change in probability. Okay, so there are some different flavors of extreme event attribution. The main ones are unconditional versus conditional, and then there's storyline approaches. So unconditional event attribution takes into account everything. It gives an overall probability change of the event, taking into account all aspects. Whereas conditional, you hold one or more aspect constant. So in practice, that means maybe you only look at events that happened with, for example, the same circulation state as the real event had. So for a heat wave, maybe there was an atmospheric blocking system. So maybe you just select the events which have blocking, or you could just select events which have a similar sea surface temperature pattern as the observed event, or the same phase of ENSO. And doing this helps to disentangle the causes of the changes in events into thermodynamic and dynamic components. So thermodynamic components have to do with temperature or are related to it. So that could be temperature itself, or it could be something like extreme precipitation, for example, is affected by how much water vapor the air can hold, and that is affected by how warm the air is. And then dynamic changes are more to do with atmospheric circulation and how that changes. So changes in thermodynamics are more certain than changes in dynamics. So climate models tend to agree more about the thermodynamic aspects of climate change, and there's a better understanding of how these things should be affected by climate change, whereas the dynamics, the atmospheric circulations, the climate models don't agree so much about this. And also there's a lot of variability, like natural variability in atmospheric dynamics. So the forced signal is pretty small compared to the variability, and also there's less understanding of how dynamics should be affected. So by, for example, looking at events which have the same circulation state as that observed, you hold this aspect constant, and that allows you to get to this aspect more clearly. But a conditional extreme event attribution method only gives a conditional probability. It doesn't give the overall change in probability of that type of event. Okay, and then storyline approaches. So this is kind of also conditional extreme event attribution, but maybe a more extreme version of it. So it involves picking apart an event and looking at the role of climate change on some aspects of it. So for example, if you have a hurricane, some aspects that you could look at would be the effect of increased water vapor holding capacity of the air on precipitation, or you could look at the effect of the warmer sea surface temperatures on the strength of the hurricane and the precipitation amount, since the sea surface temperatures are very important for powering the hurricane, or you could look at the effect of sea level rise on the storm surge. So an example of this is for Superstorm Sandy in 2012. The sea surface temperatures in that area were 1 to 1.5 degrees warmer than average. And so there were some weather forecasts that were done, sort of repeated, but without the warmer sea surface temperatures. So they just had average sea surface temperatures instead. And that allows you to look at what effect the sea surface temperatures had. So the warmer sea surface temperatures caused the depth of the storm to increase by 7.6 hectopascals. The wind speeds increased by 3.6 meters per second, and the precipitation increased by 35%. So that can also maybe give a flavor of how warmer sea surface temperatures with climate change could affect hurricanes. So a storyline approach for a drought, you could, for example, look at how the warmer temperatures affect evaporation, or you can also look at how any precipitation changes with climate change, how they would affect the drought. Yes, so as I said before, the atmospheric circulation changes are much less certain, and yes, this overlaps with conditional attribution. So again, you don't get an overall change in probability of the event, but you do kind of understand some aspects of the event and how they should be affected by climate change. Okay, so then I go a bit more into some of the methods. Okay, so the first one is the weather at home method. So just ignore this for now, I will come back to it. So the weather at home approach, it basically involves running thousands of members of a climate model of the year of interest, with and without anthropogenic forcing, and it's run on volunteers' computers, so that's why it's called weather at home. So it uses an atmosphere-only model because that's cheaper to run than a coupled one, possibly downscaled with a regional model if high resolution is important. And then for the sea surface temperatures, you prescribe the sea surface temperatures that really happened, so the observed ones. And then for the counterfactual, you also have to give it some sea surface temperatures, but you can't just give them the observed ones because they're too warm. So you have to subtract the global warming signal from the sea surface temperatures. So you can estimate that using CMIP models. So you can have a signature. So for example, it could be like this. Say these are two CMIP5 models, and this is the warming signature of the sea surface temperatures. And so you can subtract this from the observed sea surface temperatures to get your counterfactual sea surface temperatures. And you can, because different climate models have different changes in sea surface temperatures, you can actually repeat this for different sea surface temperature warming patterns. So this is also a conditional approach because you are just looking at, so the sea surface temperature pattern is similar to that observed. And so you end up with something like this. So this is a return period plot like before. This example is for 4-day precipitation in the Alba catchment. So that's actually what the second practical exercise is about, is this event in the Alba catchment, although we use different models to this. But in this case, so the red line is the ensemble with the present day forcings, and the blue is with natural forcings and natural sea surface temperatures. And in this case, actually, there's not much difference between the two. So I think the study concluded that there wasn't an obvious influence of climate change on this particular event. And you see how there's a spread in the light blue. That's the spread you get from using different sea surface temperature warming signals. But so this method was also used for the Russian heatwave example. So this example, this was using weather at home. And here you can see that there was a clear influence of climate change. Okay, and then another way of looking at it is using existing CMIP5 or CMIP6 simulations that you can download from ESGF. So you would do this by comparing models with just natural forcing or pre-industrial forcing compared to the all forcing ensembles, so the ones with the observed concentrations of greenhouse gases and aerosols and so on. You tend to have smaller ensembles by looking this way, so you don't have thousands of members like you do with weather at home, but you can get around that by taking a time slice around the date of interest. So I made a kind of pseudo figure to try and illustrate. So this is the TXX, so that's the annual maximum temperature from 1900 to present. And this is my ensemble with all forcings, and this is the ensemble with just natural forcings. So you can see that all forcing ensemble is warmer at the end of the time series than the natural one. And then you can use this to create some probability distribution functions, which you can then use to look at how the return period of your event has changed between like a natural world compared to one with the human emitted greenhouse gases. Okay, you can also do a kind of analysis with the observations. I mean, the observations is a bit harder because they are more affected by internal variability, and you can't run multiple realizations of observations. You just have one realization, so it's like you just have one ensemble member. And it's also more difficult to separate out what has caused any changes in your observations. So the climate models, you can do more idealized experiments which allow you to kind of separate out the causes better, but you can still do something. So the way that people tend to look at the observations, say you have, this is a time series of TXX from the Netherlands, so that's the annual maximum temperature. You can see that it's increasing through time, but you can fit this to a GEV, so generalized extreme value distribution, in order to estimate the return periods. And you can have global mean surface temperature as a covariate, so you can shift the GEV distribution kind of warmer or colder according to how much global warming has happened, and you can use that to look at how the return period has changed. So I'm going to talk about this in more detail in the second part of the lecture. And you can also use the same approach for transient climate model simulations. So what I mean by transient is that they kind of evolve through time. So in the same ways the observations do. So say they go from 1900 to present or into the future or whatever, but there's a time series. So you can use the same approach for simulations like the CMIP5 or 6 historical simulations, or the scenarios, or also for Cordex simulations. Okay, circulation analogs. This is something which is sometimes used for this conditional approach. So it's got to do with, you can pick days with similar circulation states as what your event had, and these are called analogs. And then if you do that for simulations with and without anthropogenic forcing, or for an earlier period and a later period, you can compare how the temperature on these days with similar circulation, how it changes between these two periods or these two types of simulations. So I tried to illustrate this visually. So here, say this is your extreme event. So it's heat wave in Southern Europe. And then you look at the atmospheric circulation pattern that occurred at the time of that event. So in this case, it was high pressure over Southern Europe. And then you look for days with similar circulation patterns. So all of these days have a similar circulation pattern. And then you can record what temperature was doing on those days. So this is the temperature that happened on these days. And then, as I said before, you can do this for the simulations with or without anthropogenic forcing, or between two different periods, and you see how the temperature on those days differs between the two sets of simulations or periods. So this is an example of this applied to a real event. So this is the cold winter of 2010. There was a very negative North Atlantic oscillation pattern. And so the question then is, how cold would this winter have been in the past with the same circulation pattern? So you can look for analogues or similar circulation patterns in the past, which also have a very negative NAO. And you can look at what the temperature was doing in those years. So this is 2010, and this is the temperature of years in the past with a similar circulation state. So you see this is actually colder, and this is the difference between the two. So this paper concluded that had this very negative NAO pattern happened in the past, that actually the winter would have been even colder than it was in winter 2010. It's also possible to look at trends in the circulation states themselves. For example, how the number of good analogues changes through time in order to get an idea of how circulation is changing. Okay, so this is the second to last slide of the first half. So this graph is showing basically that different types of events are easier or harder to attribute. And this graph is showing basically we have understanding of the effects of climate change on the event type compared to confidence in the abilities to attribute a specific event to climate change. And you will see that all the events are below the one-to-one line, meaning that you can't be more confident in attributing them than you are in understanding the effects of climate change on the event. And then all the different events have different positions on this graph, and this is determined by things like how well climate models are able to simulate the event, how good the observational record of this event is, and how good understanding of how climate change should affect the event is. So extreme heat and extreme cold are the easiest to attribute because the climate models simulate them well. We have good observational records and we understand how climate change should affect this kind of event. On the other end of the spectrum, severe convective storms, for example, those are very small and generally climate models can't simulate them very well, particularly if it's something like a tornado. We definitely can't simulate that in climate models. And also the observational record might not be that good either, because if they're small events, there's some chance you might miss them and not record them. And then you have various things in between. So for example, extreme rainfall is basically as the atmosphere warms, it can hold more water vapor. And so we expect extreme rainfall to get heavier as the world warms. But climate models don't always capture extreme rainfall very well unless they have a very high resolution. I'll just take a couple more examples. So wildfires, for example, this is something that climate models can't simulate explicitly, but you can calculate fire weather indices, which take into account things like the temperature and how dry it's been and how windy it is to get an approximation. But wildfires are also very much influenced by management strategies like fire suppression strategies, and also whether or not somebody accidentally lights a fire. So it's hard to take into account all of those things. So Yes, and then finally, I'll say something about tropical cyclones. So this is something which is a little tricky to simulate in climate models, but I think that this has improved in recent times with higher resolution, and also it's not totally clear how climate change will affect the number of tropical cyclones. There is some evidence that the strongest tropical cyclones will become more frequent. I think it was something like that, but don't quote me on it. But so yeah, there's some uncertainty about that. Okay, so this is the last slide of the first half. So I just mentioned something about rapid operational event attribution. So this is when you try to attribute an event within days of it happening, or weeks. This is to respond to questions which are asked at the time of the event. So an event happens and everybody wants to know whether climate change caused the event or how climate change affected the event. So it's an attempt to answer these questions within a time frame in which people are still interested in the event. And for this, you have to use tried and tested approaches. It's not the time to start inventing new approaches. So the World Weather Attribution Group is a group which does this. They have a website which is worth checking out. So you have all kinds of events on here. So for example, there's the heavy rainfall and floods which happened in Germany this summer. And then there's the extreme heat that there was in North America earlier in the year. So yes, I invite you to take a look at that. And so maybe we take a quick break before moving on to the second half. So the second half will be about looking at the main steps in an event attribution study in more detail based on this world weather attribution approach. And also if anyone has any questions, then please go ahead.
I think that we can have a short break. Also, there are no questions in the chat.
Okay.
Sorry. One of the computers on. So we can take a break for 10 minutes.
Okay. Okay. Right. So part two. So yes. So we'll go into some more detail of the main steps of an event attribution analysis following the world weather attribution approach. So that's what we saw on the previous slide, this rapid operational event attribution. So a lot of this is following the Pathways and Pitfalls in Event Attribution article by Gert-Jan van Oldenburg. So I put this paper in the shared materials folder. So there are a number of stages. So the first one is the analysis trigger. So that's deciding which events to study, because it's impossible to look at all of them. And then the event definition, the observational analysis, climate model evaluation, climate model analysis, then the step where you bring everything together in a synthesis statement, and then putting that into the context of vulnerability and exposure, and then finally communication. Okay, so step one, the trigger. So this is which event do we analyze? So there are too many extreme events to analyze them all, at least for this rapid event attribution analysis, it's not possible to analyze all events. So you need some way of deciding which events to analyze. So the way you could decide which events to analyze, it could be an impact related criteria. For example, you could look at events which have a certain number of deaths or people affected, or a certain amount of economic damage, either in absolute or relative terms. So for example, the World Weather Attribution people, they often analyze events which the Red Cross and Red Crescent societies launch an appeal for. Another way of choosing events to analyze is kind of demand driven. So if there's a lot of public discussion about an event and the role of climate change, or if people are asking about it, then that could be a reason to analyze the event. Or it could be that it's a record-breaking event or a near record-breaking event, which therefore makes it interesting to look at. There's also practical considerations, like whether they can perform an analysis within the given time frame. So is the manpower available? Are the appropriate model simulations available? And appropriate observations? Are there local experts that they can get into contact with who can advise about observations, for example? And you should choose an event which climate models are able to represent, at least in principle. So for example, a tornado, you wouldn't be able to attribute that because the climate models cannot capture that because it's too small. Okay, so as I said before, there's a bit of a bias in events chosen so far. So a spatial bias, for example, so people have traditionally looked at events which happen near to them. There's also a bias towards events that we expect to be affected by climate change. So maybe you're less likely to analyze an event if you think it's not going to be affected by climate change. And there's also a bias against events that are getting rarer, for example, cold waves. So if you wait until an extreme event happens, if the event is getting rarer, then there will obviously be less of them. Whereas for heat waves, they're getting more common. So then you have more of them. So you end up with less studies looking at cold waves. So these kind of biases make it a bit difficult to make a synthesis across studies. Okay, so having decided whether or not you're analysing an event which has just happened, you then have to think about the event definition. So the attribution results can be sensitive to the event definition. So it's important to document it and communicate it well. And so in practice, you have to choose the spatial and temporal definition of the event. And there's different ways of choosing this. So different approaches. So for example, you could try to maximize the signal to noise ratio, which involves choosing large spatial and long temporal scales, but this tends to be less directly relevant to the impacts. So maybe the impacts were over a smaller area and over a shorter time period. So one example of this is the first attribution study, that one by Peter Stott about the 2003 heat wave, that looked at a very large area. I think it was like half of Europe and for the whole of the summer. Whereas, so that gave a very clear signal to noise ratio and a clear result, but it's not quite the same sort of spatial scales and time scale as the main impacts of that heat wave. So another approach is to minimize the probability of the event. So choose a definition in which the event was the most rare, or another way of doing it is defining the event in a way which is related to its impacts. And this third one is the one that WWA tend to choose. So in practice, you have to decide whether you're looking at a one-day event, multiple days, a month, or a season, for example, and also the spatial scale. So are you looking at a station or a city, a region, country, larger, or maybe a river basin in the case of flooding and heavy precipitation? So some examples of an event definition could be, for example, the 1 or 3 day maximum temperature of the year. So like TXX or TX3X are just kind of shorthand ways of expressing that. Or another example could be the annual maximum 3-day precipitation over a river basin. So there's a number of choices. So for a temperature event, you could either look at temperature itself or a heat stress index which combines temperature and humidity. For flooding, there's also a number of choices. You could look at precipitation average over a drainage basin. That's probably the easiest way of looking at it, or it's possible to use a hydrological model. But flooding can be a bit complicated in that it depends a lot on things like drainage basin management, things like how much impermeable surfaces there are, whether there's reservoirs, whether there's flood defences, and also whether it had been raining beforehand, like is the soil already wet. And then drought, there's a lot of ways that you can look at drought. You can be looking at a precipitation deficit only, or you can include information on evaporation or soil moisture, or even water availability in rivers, reservoirs and groundwater. So it gets more complicated as you include more things. And you have to think about which things the climate models can simulate and which things you have observations for. Oh, that's what I just said. Okay. And then you also have to think about the framing. So generally in world weather attribution studies, they're looking at all events the same size or larger than the one that was observed. So this is called a class-based framing. And then also you have to decide whether it's a conditional event attribution study or an unconditional one. So are we only considering events with a certain phase of ENSO or similar atmospheric circulation conditions to that observed? And then pinning down what actually happened is not always straightforward, especially straight after an event when not all the data has been released yet. So an example, this is from the Pathways and Pitfalls article, the Hurricane Harvey in Texas in 2017. This is 4 different observational data sets looking at the 3-day maximum precipitation during this event, and you can see that they're quite different. So particularly the satellite, this one's a satellite, that one's particularly different. This one's the radar, this is station data, and this is a gridded station data set. So they say that the radar is likely the most accurate, but it only has data going back to 2005, so it's not long enough to do an event attribution study with. So in the end, they chose these 2. Which brings me nicely on to the observational based analysis. So generally WWA, they do an observational based analysis as well as the climate model analysis, just as a, I guess, a verification type thing. So for this, you need a long time series, preferably from at least 1950 or preferably longer. It has to include the event in question. It should be as homogeneous as possible and not influenced by other factors like changes in the station or urbanization kind of encroaching. And local expertise can help identifying the best data, and you can of course repeat with more than one data set to test sensitivity to the choice of data set. So looking at the observations allows you to estimate the probability of the event in the current climate, and also to estimate how the probability has changed. And the observations are also needed to evaluate the climate models and for a possible bias correction of climate models. So many climate extremes are already showing Sorry, I seem to lost the connection or something.
We did.
Sorry for this interruption. We had a problem with the internet.
Okay.
To share.
Okay. So we have to start again.
Sorry.
That's right. Okay, I can share again. I don't know which point I had got to when you dropped out. we can see.
Yes, this was the.
Yeah, you actually finished with explaining the purpose and then went on to this slide and it stopped.
Yes, right.
Okay.
Yes.
Right, we didn't miss very much then.
Okay.
Yes, I just said that many climate extremes are already showing trends due to global warming. And then I was about to go on to the methods for the observational time series. Okay, so this is basically, okay, here's a time series of TXX from the Netherlands, so that's the annual maximum temperature. And so you fit an extreme value distribution to this data and you allow it to shift with global mean surface temperature. So global mean surface temperature is a covariate, and I've made some diagrams to try and illustrate this. Oh, nothing's happening. Okay, now it is. Let me move this panel out the way again. Okay, so here's my GEV for 2021. So what always confused me initially was how do you have a distribution for 2021 when 2021 is only 1 year, but actually it's that this whole time series is used to make this distribution, but it's kind of global mean surface temperature is used as a covariate, so you can adjust all the data as if it happened in 2021. And then you can also, so there's a threshold that for the event that happens, so this is the probability of exceeding that threshold in 2021. And then you can shift this distribution cooler when you look further into the past. So this, for example, could be 1950. So now you see that you cross this threshold less often. And then this is 1900. And so now you don't pass the threshold at all. And for precipitation, okay, here's the distribution in 2021. So the distribution is a bit of a different shape. For precipitation, here's my thresholds. So here, these are all the events that pass the threshold. And for precipitation, actually, the distribution is more of a multiplicative change. So maybe it looks like this at previous dates. And you see how the probability
Oh gosh.
Что покажет?
Опять.
Опять.
Sorry. Ja, ne, što da kažem.
It seems we are experiencing some problems with the connection.
No worries. Okay, let me share again. Oh, it says host disabled participant screen sharing.
We have to repeat that step every time.
Okay, this looks like it might work this time. So where did we get to this time? Was I on this slide?
One before, I think. Yeah,
This one.
with the distribution, you started explaining precipitation extremes and it stopped. So
Okay.
Okay.
So I do the precipitation again. The changing amount of missing data over time, you can get spurious risk ratios. So for example, if you have a lot of missing data at the beginning and none missing at the end, it can give you a positive risk ratio, suggesting that your events become more frequent just because you were missing events at the beginning because you were missing data. And also spatially interpolated data sets, they might look spatially complete, but they actually may also miss extremes because you don't generate extremes in the areas where you have no data. You tend to kind of smooth across those areas. So it's worth checking how much data is going into gridded products. And for some things, reanalyses can be better in the sense that reanalyses are able to generate extremes between data points. So here's an example of, this is showing the trend in May maximum temperature in a data set. This is an observational data set called CRU TS4, and it's suggesting that there's a warming. But then if you look at how many stations are going into this, there's really not very many stations over India compared to some of the surrounding areas. And if you look instead at Area 5, which is a reanalysis, you actually see that there's a cooling trend, which is due to irrigation, but this was totally missed because of the poor data coverage. Okay, so the findings of observational based analysis, you tend to find clear warming trends for heat waves and also significant warming trends for cold waves, although cold waves tend to have, basically there's more variability in winter, so it's harder to detect a signal. Daily to subdaily precipitation extremes also have clear trends towards getting more intense, but for longer duration precipitation extremes, the signal is more mixed. It depends more on changes in atmospheric circulation. And droughts, these are longer term events, often multi-year, which decreases the sample size, so that makes them more difficult to look at. Okay, so that was observational analysis. So now we move on to models. So the observations alone can't tell us what caused the trend. We need climate models. But that, and also climate models, allow us to get a better signal to noise ratio by running ensembles. But first of all, you have to evaluate the models to check that they are fit for purpose. And you do that using the observations. But first of all, you have to ask yourself whether the model can, in principle, represent the extreme that you're interested in. So for example, for hurricanes, you need at least 25-kilometer resolution. If you're looking at convective rainfall, then you need less than 4-kilometer resolution, so that's really high resolution. For heat extremes, it's less important to have high resolution, so 200 kilometers is probably still okay. And sometimes you have to think about things like if you're looking at an area in which there's a lot of irrigation, does your climate model capture that? That can be important for heat extremes. Probably the model doesn't have this in. And then you can evaluate the statistical distribution of the extreme events in the climate model and see if it's similar to the observed one. So this is where the GUV parameters come in. You can compare them to the observed ones and check that they are similar. And you need good observations in order to validate the models, because otherwise you may discard models which are actually perfectly good if the observations are themselves not that good. You can also evaluate whether the meteorology leading to the extreme you're interested in is represented okay in the model compared to the observations. So for example, you can look at the seasonal cycle or spatial patterns. You can look at whether the ENSO teleconnections are represented well, if ENSO is important in the region that you're looking at, or for the extreme that you're looking at. For heat waves, blocking is often important, but climate models often underestimate blocking frequency, so that's one thing that could be checked. And another example is in places affected by hurricanes, if you're looking at extreme precipitation, do you have the correct proportion of extreme precipitation coming from hurricanes versus coming from other things, other weather systems? So WWA, they basically collect as many climate model ensembles as possible, as not all of them will pass these validation tests. And then they keep only the models that pass the tests. And they require at least 2 models in order to proceed. Otherwise, they just make a statement based on the observations. Here's some examples of things that can be badly represented in climate models. So in this particular climate model, Mirok ESM, this is showing the average hottest day of the year, and you see that in some places you have more than 70 degrees Celsius, which is probably not that realistic. Another thing which can not be represented well is some models have an unphysical cutoff for heavy precipitation at about 200 to 300 millimeters per day, so the models can't simulate precipitation any heavier than that. So in these plots, this is showing the 3 different models. They're return period plots of the annual maximum precipitation over India, and this magenta line, that's the observed event, and you see that the climate model is not able to get up that high, even though the distribution fitted to the rest of the data suggests that it should. It doesn't manage it. Okay, and then this is an example of what I said before, where in the observations you have irrigation, which is actually causing a cooling trend in annual maximum temperature, but CMIP5 models, for example, don't include irrigation, so you have a warming signal, so they disagree. Okay, so then once you've evaluated your climate models, you can do the attribution step using them. So you can either run 2 ensembles with and without anthropogenic forcing, and then you could either just count the number of events in both, which are the same size as or bigger than the one that you observed, or you can fit a distribution in order to calculate the return periods. Or you can use the same method as for the observations. So you can fit a GEV, which shifts with global mean temperature. And so models can have biases, but it's possible to overcome this to a certain extent by using, you can select an event which has the same return period in the model as in the observation. So say, for example, you have an event which was 38 degrees in the observations, and that's a 1 in 20 year event. It might be that in the model, the 1 in 20 year event is cooler, maybe it's 37 degrees, but that doesn't matter if we just pick an event with the same return period. This kind of just overcomes that issue, and it can be less problematic than doing a full bias correction. Okay, and so then when you have your results for all the models and for all the observational data sets, and then you want to bring them all together into an attribution statement. So yes, we end up with a probability ratio and change in intensity for each model, an observational data set, and you can basically, the results for the world weather attribution studies, they tend to look like this. So this particular one is for extreme 3-day precipitation in 2016 for the Seine in France, when there were floods, and you get a diagram that looks like this. So you have, this is showing the probability ratio, and then you have different estimates. So the blue one is the observations, and then there's 4 different model ensembles, and then the magenta one is a kind of weighted average of the above. So you see in this example that the model estimates, they overlap with the observed ones, and they're fairly consistent with each other. So this is an example where the different lines of evidence agree quite well, and then your final statement will be that these floods were basically a bit more than 2 times as likely in 2016 as they would have been without climate change, with an uncertainty range of 1 point something to about 4. So here's another example, and this time this is expressed in intensity change rather than probability ratio. So this is for extreme 3-day precipitation for Hurricane Harvey in 2017. So this time we have lots of different observational estimates. So there were 2 observational data sets, and then there's different ways of looking at those observational data sets. And then you have 2 different climate models. So in this case, the climate models agree less well with each other, although both of them overlap with the observations. And this is the synthesized average. So the event was about 15 times 15% stronger than it would have been without climate change, with an uncertainty range of 8 to 20. And if you want to know the details of how this is calculated, because it's a little complicated, I've put a link here which explains the details in case you ever want to do this and you want to find out more about it. And then here's another example. So this is for Storm Frederica in January 2018, showing wind intensity. So in this case, the observations and models actually disagree. So the observations are suggesting that this that wind intensity, like what was observed in Storm Frederica, should actually become less likely, or has become less likely than it would have been in the past, whereas the climate models are suggesting that it should have become more likely. And this is likely due to a missing process in the climate models, like surface roughness length, for example. So that has to do with trees and buildings, which kind of slow the wind down. So maybe these models don't include those sorts of changes. So in this case, WWA, they actually, I think they didn't make a attribution statement because the models and observations were just so different. Okay, then the penultimate step. So once you've got your attribution statement, you then put it in the context of vulnerability and exposure. So vulnerability and exposure can be very important in determining how much impact the event had. So in this diagram, we have the hazard. So that's the hydrometeorological event, so the heat wave, heavy rainfall, hurricane, or whatever. And then you have exposure, which is to do with the people, properties, ecosystems, and so on, which are in the path of the hazard. And then vulnerability is how susceptible the exposed populations, systems, assets, and so on are to the damaging effects of the hazard. So for example, if you had a heat wave, but everybody had air conditioning, then they're less vulnerable. Or if you have an aging population and you have a heat wave, then they're more vulnerable. And so exposure and vulnerability can change through time. So for example, after the 2003 heat wave, Paris came up with like a strategy to cope with heat waves, and so subsequent heat waves have had reduced deaths compared to 2003. Another example is a drought in Sao Paulo in 2014 to 15. So the attribution analysis showed that climate change didn't have much role in the water shortages, but population growth and increased water use per capita did have an important role. And so often this vulnerability and exposure information is used to make a qualitative statement which puts the results of the attribution analysis in context. It's quite difficult to get quantitative data about exposure and vulnerability, so that's why it's often a qualitative statement. And then finally, the last step is communicating the results. So there's various types of communication for different audiences. So different audiences could be scientists, policymakers, emergency management agencies, media outlets, and the general public. So WWA, they make a full scientific report or a peer-reviewed article to document in detail what they did. And the idea is that it should be reproducible by anyone who wants to reproduce it. And then they also have a 2-page scientific summary with the main graphs for people who, are interested, but they don't want to read the whole study. And then they make briefing notes and also a press release for the media. So in summary, this world weather attribution, it allows rapid attribution after an extreme event. For example, a few days or weeks after the event. They've been doing this for 5 years now, so it's quite new actually. And the results can be useful for adaptation planning, raising the awareness of the need for mitigation, and it also provides a scientific answer to a question that would otherwise be answered unscientifically, i.e. how did climate change affect this event? So I put a couple of papers in the shared folder. So the first one is by Peter Stott, and it's basically just introducing the extreme event attribution and some of the main methods. So it's kind of like the first half of the lecture. And then the second one by Gert-Jan van Oldenburg, this pathways and pitfalls in extreme event attribution, that's like the second half of the lecture. And then you can find some examples of event attribution studies on the World Weather Attribution website, or also in the BAMS supplement. And so it's worth looking at a couple of those. So I think that's all I have to say about the lecture. I don't know if anyone has questions.
So far, nothing in the chat. I don't know, maybe we can ask people to unmute and ask the question directly, or if they feel more comfortable, they can write the question in the chat and we can answer it. You can answer it later, or I don't know. Yeah,
just feel free to either write it or put your hand up or just talk. Yeah.
So still nothing in the chat. Maybe we can have a short break and continue with the practical part, or is this the plan? The practical part is now on. Yes. And then probably will be more questions when we start working on this practical thing rather than theoretical. So maybe we will have more questions then.
Yeah.
So should we have 15-minute break, or what is your suggestion? 15 minutes. Good. Okay, so 10:45 we will be back.
Okay.
See you soon.
See you later.
Okay, I think that we can continue. I hope that everyone prepared themselves a coffee, so they can continue with the good work. So Carley, please help us with the practical part.
Right. So I'll share my screen again. That's the end. Hang on.
Emanuel se uključio.
Pa dodala sam.
Okay, so yes, this is the practical part. So we will attribute the heat wave, the 2007 heat wave that happened in Serbia using Climate Explorer. So this heat wave in 2007 was a record-breaking heat wave. So for example, the temperature was 43.6 in Belgrade. And so we're going to look at how this event was affected by climate change, and we will use Climate Explorer to do this. So using Climate Explorer, we will do a number of steps. So we'll start off by looking at maps and time series of the event in observational data to see what's happened. And then we'll look at, we'll work out what the probability of the event is in the current climates and how this has changed compared to 1900 using station data. And then we will look at a climate model and we'll validate it with observational data to see if it's fit for use. And then we will repeat the attribution analysis with the climate model. And then we will synthesize the results into an attribution statement. Oh yeah, there's also the second example, so we probably won't get onto that, but just it's there in the shared folder in case you're interested. This was a flooding event in the Elbe and Danube basins in 2013, just as an example of a different kind of event. So the goals are partly to introduce Climate Explorer, which is quite a useful tool, especially if you want to have a quick look at something, or if you have a student who wants to have a quick look at something and doesn't want to get into coding. But then of course the second goal is to understand how to carry out an event attribution study in practice. So a real life rapid attribution study takes a team of researchers at least a week. So this is of course a stripped down version since we don't have a week. So we're looking at one model and one observational data set instead of using multiple models and observational data sets. And if we were doing this for real, we would also take more care over the various steps, like how to make the event definition, quality control of the data, and so on. So this is what Climate Explorer looks like. So you should log in or register if you haven't already registered. And that will allow you to access the full functionality of Climate Explorer. So otherwise you can't do everything that you need to. So when you use Climate Explorer, sometimes you'll find the steps that you're looking for, or the analysis, the steps that you're looking for on this side, or sometimes if they're not there, they can be at the bottom in kind of blue boxes with various options you can tick. So yes, as I said, please log in. And if you log in, it keeps any time series that you calculate for 3 days. If you want them to keep them for longer, then you have to download them. So hopefully I don't need backup plans this time. When I was doing this with the early career researchers, I wasn't too sure how many people Climate Explorer could cope with, but actually we didn't have any problems. So I think this should be okay, but if something doesn't work, then please let me know. You may get this error message come up. So when we were testing this with colleagues here at Cicero, sometimes if multiple people calculate the same thing at the same time, you get this message, but it doesn't actually seem to matter. You can just carry on. But obviously let me know if it doesn't work for some reason. And for some steps, I've also uploaded to the shared folder some pre-calculated time series, which if for some reason you can't get Climate Explorer to calculate something, then you can just upload the pre-calculated version instead. And so I've said all this in the instruction sheet. Oh yeah, that was for later. So I will just share the instruction sheet just a second. So let me share again. This one. That's the end of it. Okay, so you will find an instruction sheet in the shared folder. So this is adapted from some instructions I got from the World Weather Attribution people. So initially this was for the 2018 heatwave in Europe. So I changed it to the 2007 Serbian heatwave just to make it a bit more relevant to you guys. So I got permission to use these adapted instructions for the workshop, but I do ask that you don't distribute them further than this. Hang on, where's my cheat sheet gone? Just need to remind myself what I wanted to say. Let me think. So the way we did this last time is we kind of went through by sections. So you'll see that there's different steps for different numbers. So it starts at step 2, which I suppose is a little illogical, but that's just the way it is. And so we went through a certain number of steps, and then people let me know when they'd done it, and then we all got together and talked about it. So we can try doing something like that again. I mean, if you are online, you can just write in the chat when you're done, perhaps. So we will, so we'll start off by looking at some observational data. So we're going to plot some maps to look at what the event was like. So like this, for example, so you can just work through and the instructions will take you through, and then we can talk about it. So we will use this variable tx3x as our event variable. So that's the annual maximum of 3-day averaged temperatures. So basically it's the 3 hottest days of the year for 3 consecutive days. Yes, so maybe, I don't know if I forgot to say something, probably, but never mind. But if you could do all of step 2, and then let me know when you get to here, so up to step 3, so not including step 3, just step 2. Does that sound okay?
With the interpretation.
Yeah. That sounds good to me.
Okay, I can share then our results.
Okay.
Let me just. Okay. This is the first figure that we get, and this is the actually shows the climatology of 2007 and how 2007 was compared to the other years in the time series. So it was actually hotter. Let me just. It was actually hotter by almost 3 to 4 degrees in some areas of Southeast Europe, and in the eastern parts at up to 5 degrees hotter than previous years. That is the first map.
Okay, yeah, so that's compared to, oh, sorry, I'm muted. Oh no, I'm not muted. Yeah, so that's compared to the maximum temperatures in other years. That was just one point that.
Is it possible to just maybe not to take the whole investigated period as a base period for calculating climatology? Maybe we can use some, I don't know, recent base periods like 81 to 2010 or something like that. Maybe we could see, this picture would probably be different then.
Yeah, you can also do that. I'm just trying to find my the right place in the instructions. Sorry, I've got 2 screens, so I'm getting a bit confused. So what did we do this relative to? Was that the whole time period?
Yeah, so is it advisable to use the reference time base periods that World Meteorological Organization actually suggests, or to have the whole period? What is the better option when doing these studies?
Well, you could do either, I think. I mean, in this particular case, no, hang on, I'm thinking of the wrong plot. Yeah, I mean, it's up to you. I guess it is kind of more conventional to do it relative to a 30-year period like the World Meteorological thing. I think you just decide on a case-by-case basis what you want to do. So either is an option.
Okay. This is the second map. It actually shows the rank, let me just rotate it, rank of 2007 compared to other years in the time series. And it actually says that the 2007 was the hottest year on record for some period, some parts of Southeastern Europe and the eastern parts. And here in Serbia, it's actually between the second and the fourth and the third year, the hottest year on record. So it would be really nice to find that first one for the whole Serbia.
Yeah, that would be interesting to know which the first one was.
Yeah, so maybe we can play a little bit later with this. So yeah.
Yeah. So yes, that looks how I was expecting it to. Yeah, that looks good. In this case, looking at the longer time period, the whole time period, is actually kind of informative, because we see that in a lot of places this was the hottest heat wave even in the 70-year period, so not even just compared to 30 years.
Yeah.
Even compared to more recent years as well, because this is going up to 2020, and obviously that heat wave was 2007, so in some places there hasn't been a hotter heat wave than that since
then. Yeah, it's really interesting.
Yeah.
The third map was the climatology for July, if I remember correctly, and it actually shows the monthly mean of daily maximum temperatures in July compared to other years. And it shows that those July temperatures were actually hotter and higher, up to 5 degrees than other years, as we saw. But here also in Norway we have a great anomaly. Yeah. So
yeah, I hadn't noticed that. Cool. Yep, that looks good.
And the last one is actually the mean summer temperature, maximum summer temperatures in 2007. And those are actually the measured temperatures in this case, not in the climatology. And it shows that the temperatures were as high as 27 or 30 degrees during the summer period. And we can see here the Carpathians, the Alps, and the other mountains here.
Yeah, so actually this is the climatological mean over the longer period for the whole summer. So it's not actually 2007, this is the average for the average summer across all the way from 1950 to 2020.
Sorry.
It's all right. Just to see what an average summer is like. So we will compare that to the same from a climate model later as a model validation step.
And that's the last map that we produced.
Okay. Yes, that's
I'll stop sharing my screen.
Okay. Yeah, thanks very much for sharing the screen. Okay, so then I will, well, I mean, first, does anybody have any questions about what we did so far?
Nothing. So,
okay, no worries. So then I will share my screen again. Oh dear, I can't find the instructions. Where are they? Oh, this is it. Yes. Okay. So, okay, then we can move on to the next step. So, in this step, we will, just looking at my notes to myself. So, yeah, so we will get a time series for Novi using station data. And then we're going to just look at the time series to check that there's nothing obviously strange about it, no weird things going on. And also we have a plot of the annual cycle, which we can compare to the same in the climate model. I think actually we don't do that in this practical, but we could. And this can be more important if you're looking at precipitation, because sometimes a climate model could have the peak precipitation at the wrong time of year, for example. And then we'll plot a time series of the days leading up to the event and then the event itself and the days afterwards, just to have a look at it and how long it lasted. And we can also think about whether this TX3X is an appropriate index or whether we could have used something else. And then we'll calculate the time series of TX3X and have a look at it and talk about that. And then we can also check whether the variability changes through time by plotting a running 15-year standard deviation of TX3X. And so then we can get back together again. So if you can do up to 3.7, so that's until, so we don't do the GUV fitting just yet. We'll do that afterwards.
Imamo 10
minuta, možemo.
So,
okay, we have 10 minutes until lunch break.
oh yeah, of course.
Maybe we can start with this and then have a break and then come back and maybe show the results and continue with GEV distribution. What do you think?
Yeah, Yes, I temporarily forgot about the lunch break, so it's good that you reminded me. So yeah, we can, it's at 12, right, the lunch break?
Yeah, it's well.
Okay, and when do we come back?
At 1:30, we have a lunch break until 1:30, and then come back and finish with the practical part. So maybe
Okay.
we can continue with this until 12, and then go on lunch break, come back and show what we did until this step fitting GEV distribution.
Yep.
Okay.
Sounds good.
We can continue. So yeah.
Okay.
Okay.